Let's look at a hands-on example that demonstrates exactly what a CPU bottleneck looks like in Node.js. The example uses the Fibonacci sequence. It's a classic, admittedly over-criticized example, but it is perfect for illustrating what happens when your JavaScript code performs a CPU-intensive synchronous task on every incoming request. Here's the setup. We create a simple HTTP server using Node's built-in HTTP module. On every incoming request, instead of doing something lightweight, we call a recursive Fibonacci function with the argument 40, Fibonacci of 40. The function itself is purely recursive, calling itself with n1 and n2 on every invocation. No memoization, no iteration, just raw recursion. Here's the code: var http equals require, http, var server equals http.createServer, server.on, request, function, req, res, var f equals Fibonacci, 40, return res.end, plus f, server.listen, 3000, function Fibonacci, n, return, n less than 2? N, Fibonacci, and 1, plus Fibonacci, and a 2. We start this server with the prof flag to tell V8 we want a profile log, $node prof_fib.js, then we benchmark it using Apache Bench with just 10 requests and 2 concurrent connections, $aben10c2 http //localhost 3000 / the results are brutal. Time taken for tests, 18.851 seconds. That's almost 2 seconds per request. Requests per second, 0.52. Half a request per second. For a server that is doing nothing except computing a number. After stopping the server, you'll find an isolate star.log file in your working directory. This is the raw V8 profiling tick data. You open it with the V8 tick processor, available online at v8.googlecode.com or in your Node.js source at dep/v8/tools/tick processor.html. The output tells you clearly, 89.1% of all CPU ticks belong to the Fibonacci function. The bottom-up profile shows the same function repeated at every level of indentation, that is the recursive call pattern made visible in data. Now we have confirmed the problem through profiling. The Fibonacci function is consuming 89.1% of all CPU ticks. The next question is, what do we do about it? The book offers 2 approaches. For complex operations, you might restructure the code using patterns from earlier chapters, things like breaking work into smaller pieces, using worker processes, or offloading to a queue. But for this specific case, there is a much simpler one available: memoization. Memoization is a technique where you wrap a function and cache its return values based on its arguments. If the same function is called again with the same arguments, you return the cached result instead of recomputing it. For a pure function, one whose output depends entirely on its inputs, with no side effects, this is completely safe and dramatically effective. Here is the updated code: Fibonacci equals memoize, Fibonacci, function memoize, f, var cache equals, return function memoized, n, return cache, n equals f, n. The key thing here is that we overwrite the Fibonacci reference with the memoized version. This is critical because Fibonacci calls itself recursively. If we did not overwrite the reference, recursive calls would still hit the original unmemoized function. By replacing the reference, every recursive call also gets the benefit of the cache. The performance result is dramatic. Running the same benchmark, 10 requests, 2 concurrent, now returns, time taken for tests, 0.038 seconds. Requests per second, 263.86. That is a jump from 0.52 requests per second to 263 requests per second. More than a 500x improvement, from one change. If you now run this memoized version through the V8 tick processor, the Fibonacci function has essentially vanished from the profile. The ticks are now distributed across HTTP machinery, socket handling, stream internals, the normal Node.js infrastructure, with no single function dominating. That is what a healthy profile looks like. When you look at your own profile and see one function owning 80 or 90% of ticks, that is your immediate optimization target. Let's talk about how to actually use the V8 profiling tools and how to interpret the tick processor output, because understanding the raw data is essential before we move on to flame graphs. When you run Node.js with the prof flag, V8 activates its statistical profiler. This profiler works by taking samples, called ticks, at regular intervals. On each tick, it records the current call stack. After your program ends, or after enough ticks accumulate, the data is written to a file named isolatesomething.log in your current directory. The V8 tick processor reads that log and produces a human-readable report. There are 2 key sections to understand. The first is the JavaScript section, which shows each JavaScript function along with its tick count, the percentage of total ticks it represents, and its non-lib percentage, the share of ticks excluding library code. When Fibonacci shows 14,267 ticks at 89.1% of total ticks, that is an unambiguous signal. That single function is consuming almost all available CPU time. The second is the bottom-up, heavy, profile. This shows call chains in reverse. The function at the top is the one that was actually running when the tick was sampled. Below it are the functions that called it. In our Fibonacci example, every level of the bottom-up profile shows Fibonacci because the call stack at every sample was Fibonacci calling Fibonacci, all the way down. You can count the levels of indentation and visualize the recursion depth. A few practical notes. When running your own benchmarks, restrict the server to only the duration of the benchmark. If you leave it running longer, idle time gets mixed into your profiling data and skews the percentages. Keep the benchmark tight and the profiling period focused. Also note that there is a spectrum here. If a function shows 89% of ticks, that is a clear win to optimize. If the ticks are spread across dozens of functions each at 2 to 5%, that is a healthy distribution and there may be no single optimization that moves the needle significantly. That is normal production behavior and you can confirm it with the memoized versions profile, where no single function stands out.